It is our pleasure that the second speaker in this session is Professor Özgür Müstecaplıoğlu from Koç University. He's also a senior researcher at TÜBİTAK Research Institute for Fundamental Sciences. He's a wonderful scientist and a great friend. We also know Professor Özgür Müstecaplıoğlu from the first part of our school, where he gave an excellent lecture on Introduction to Quantum Sensing. Now he's going to talk about quantum technologies for human vision. Özgür Müstecaplıoğlu received his BC in physics as well as his PhD on quantum optics from Bilkent University. His research involves theoretical studies in interdisciplinary areas covering quantum optics, optical properties of semiconductors, foundations of quantum electrodynamics, atomic Bose-Einstein condensate, quantum information science and technology, and nonlinear optics. So, Özgür Hocam, please come and continue.
Thank you so much, Alikram Bey. And I'm happy to continue my talk in the direction of quantum sensing. So in the workshop, I will be a little bit more technical, but hopefully our students will have a chance to see application of what we have discussed in the lectures. I hope you can see my shared screen, and if there is any problem, let me know. So we are going to talk about application of quantum metrology and quantum sensing technologies for understanding human visual system. So we learn a lot of quantum optics in our undergraduate and graduate studies. We take courses, read books, but mostly we use artificial or synthetic devices to detect the light and make our quantum interferometric measurements. But the first thing we interact with the light is actually, as a human being, is through our own eyes. So understanding of light interaction with the human eye at the quantum level is actually both fundamental and interesting question with lots of interdisciplinary touches. So I want to, first of all, thank my students that I collaborate in this direction of research. So we have 3 students. 2 of them are PhD students at Koç University, Lia Gassap and Ali Pedram. And we also have a Master of Science student, Baran Hökelek, also at Koç University. So as I said, this is quite an interdisciplinary direction of application of quantum technologies with many interesting facets. So we consult heavily to Department of Psychology at Bilkent University. There's an excellent professor, Hüseyin Boyacı, there on this topic. He has also some physics background. He was my classmate at Bilkent Physics Department. Then he changed into visual system analysis from psychological point of view. And he helps us to understand psychophysical experiments when humans are involved in quantum optical measurements. And Professor Yannis Kominis at the University of Crete in Greece has a nice experimental facility that can do some experiments using the human eye and also using optical quantum systems. So we also consult him for experimental parts of our studies. So this is the team. Our research is funded by TÜBİTAK 1001 program, and then we also acknowledge their generous support. So of course, this is a general topic when you talk about applications and the implications of quantum technologies for the human vision. There are different directions of approach. Our approach will be a little bit more fundamental at the level of understanding the human visual system using the quantum light. So the general topic is, of course, human vision is the act of seeing. Of course, here when we say act of seeing, the definition of seeing itself is a little bit confusing. So because whether we see at the level of retina or we see at the level of brain perception of what we see, shapes and the images, they are different questions. So when we talk about act of seeing, we will usually approach the act of seeing at the retina, and we will distinguish it from what we perceive in our neural network in our brains. And of course, when you talk about act of seeing, first of all, you need light. Yes, and how to talk about quantum technologies related to an act of seeing or vision, we have to think about quantum light. So quantum of light is photon, and this is technologies related to quantum of light is called in general photonic technologies. Okay, but then the obvious question immediately emerges when we turn off the light. When everything goes dark, the act of seeing immediately becomes quite troublesome. Yes, so we have quite a low ability to see in dim light conditions. But unfortunately, photonic technologies are based upon to operate. We have single photon sources, we have entangled pairwise photon creators, but they just have a very few number of photons. So quantum photonics of light basically based upon dim light conditions, where our human eyes, our natural detectors, have some uncomfortable properties, low efficiencies under such dim light conditions. So the question of can we really see quantum light becomes important at the very beginning. Well, of course, it was a dream to see in the dark. If you look at the literature of folk tales and fiction, you can see a lot of examples where there are creatures, not humans, can see in the dark. Okay, so they help to humans sometimes when they travel in the dark caves. These creatures like dwarves helps the humans to let them go through. Okay, but do we really need help of mythical creatures? Can our own eyes as a human being are really that bad to see in the dark? Is an interesting question. So let's compare ourselves not with the mythical creatures, but actual animals that can do better than us in dim light conditions. So their eyes seems more adapted to see in the night in comparison to humans. Okay. So one important advantage these nocturnal or night vision ability animals is that their ability to see the spectrum of light is far developed than ourselves. So we have our eyes are not suitable to see infrared light or ultraviolet light. We have to protect our eyes even under such conditions of UV and so on. But we see only very narrow range of spectrum, which is known as visible light spectrum. It's a very narrow region of available electromagnetic spectrum. But nocturnal animals can detect the infrared light in the night much better than us. So this is one advantage they have. The other advantage that they have is that their structure of their photodetectors or their eyes are also designed to operate in night or dim light conditions. So our biological disadvantage is the following, that our lens or our cornea, which is fixed part of our focus system. So we have basically two objects in our eyes, the cornea, which is fixed, and also the lens, which is attached to the eye through some muscles. So it is adaptive. So we can focus the incoming light, but we can only do it very poorly actually compared to night vision animals. So if you look at night vision animals, they have very large lens and very large pupil, and they can collect more light much effectively than us. Okay. So let's look at the point that let's look at a little bit more macroscopically what is the effect, how we collect this light. Okay. So of course, this is macroscopic description. If you just look at the cornea and the lens, this just try to focus the light on some region, and this region is called retina. Okay. And on this retina, actually, there is some very interesting macroscopical vision process happens. And there are antenna-like objects, some cells known as rod cells and cone cells that they interact with this incoming light. Okay. So these rod cells that you can see in this picture here, they are just elongated tubular structures. Okay. So at the right-hand side, you see some slits. Actually, they are discs. Okay. So lots of discs here. So in these discs, there are some photopigments. They interact with the light, and one in reason that they are able to interact with the light, there is a photosensitive pigment on this disk, which is rhodopsin. Okay, so there are also quantum models of rhodopsin, how it interacts with the light. I will not go into these models here. We will not go into that microscopical. We will approach them as some tiny antennas, and what happens that these rod cells are sensitive to light collectors, while there are also other objects that I don't show it here. They are called cone cells. Okay, so their distribution in the retina are different. So these rod cells are usually in the peripheral region of the retina, while the cone cells are in the central region of the retina. And they have two important differences. These rod cells are sensitive to light, and they can collect the dim light conditions. They can operate in the dim light conditions, while the cone cells make refinements on what we see, and they can interact with the color light, and they help our color vision. Okay, but in the darkness, the color is not very important. So during my talk, you will hear more often the rod cells than the cone cells. Okay, so this refinement of the shape, or it is color, is not the big question for color for night vision. For us, it is enough to distinguish the brightness and darkness, and rod cells are the main element of photosensitive cells for our purposes. Okay, so if you look at this picture before, so in addition to this macroscopical shape advantage, where they have larger lens and collect more light, when the light falls into the retina after it focuses on the retina more effectively in nocturnal animals, you can also say that nocturnal animals have more collectors, photo antenna cells like rod cells, than our cells. Okay, so in humans, number of the rod cells are not that much, even though they are more than the cone cells. We have still fair. We are not doing as much as good as for the nocturnal animals. So they have different microscopical and macroscopical advantages when it comes to structure of their photodetectors or eyes. So one more structural advantage they have, even if they collect larger amount of light in the night than us, they even amplify it with an interesting additional layer in their eye structure. Okay, so if you look at again this picture, you can see that there are some layers at the back side of the eye. This hole here is just the nerve system that goes to the brain, and there are additional layers here. And one of these layers do not exist in the humans. Okay, this layer is known as tapetum lucidum. It's just a tissue. It just helps to reflect the light. Okay, so when you just shine light on the eye of a nocturnal animal, you will see that it will glow in the dark. It can be scary if you imagine in forest you can see some shiny eyes looking at you. Then if it's a hunter animal, then you are in trouble. So it's sometimes scary, but humans don't do this. If you just hold the torchlight on your eyes, your light will not shine. The reason is that we lack this additional tapetum lucidum tissue layer. Okay, so another advantage is that they have natural amplifiers. So they have a big lens, and also they have more rod cells. These are their advantages. But what we do is that why we rule the planet, not the animals, because we learn from them and we can do better from them by designing synthetic devices. So in the night vision, when we learn this structure of the nocturnal vision from animals, we can try to make even better than them by designing some night vision devices. For example, we can typically, instead of this tissue of reflective tissue that we lack, we can just add this amplifiers in our eyeglasses and make some night vision goggles, night vision devices using this kind of artificial layers, and they make also access to larger range of electromagnetic spectrum, especially infrared spectrum, to design infrared detectors with that kind of designs. Okay, so this is not a quantum technology, this is classical technology, but it is some ability enhancement for humans that we can improve our vision to the dim light conditions. But this doesn't mean that we can see in the dark. We need additional devices. Okay. But what I want to ask here, if I don't want to use any artificial reflectors, amplifiers, image enhancers, and so on, if I don't want to access the larger spectral range, can I still hope that I can see something in the dark? Okay. Or this is basically one of our research direction questions that I want to ask more quantitatively, how low dim light I can detect without using any of these this military quality enhanced Googles. Yeah, so this is one of the questions that I'm going to address here. So let's look at the mechanism of seeing more closely to understand how we can see and what's the level of threshold of dim light conditions that we can see. And to answer this question, let's also once again emphasize the definition of seeing should be understood carefully, that we have two possibilities. So when the light arrives to the light, you can detect it at the retina level and then change the light energy into electrical signal or neuron signal. It will propagate to the brain, and then you will say that I have seen something. Okay, so this is actually called perception. Well, here we have the seeing of or detecting the light. Okay, and we can expect there are at least two different thresholds to see the dim light conditions. So you may need a different number of photons, different intensity levels to say that the light is detected and observed here, while the brain may need larger threshold to really say, aha, I have seen something. Okay, so we might expect two different thresholds for the light in these conditions. So I want to also say, in relation to Angelo's beautiful talk here at this stage, so if I have dim light conditions, just let's say the quantum of light is few photons, low intensity means you have less number of photons. But during his talk, Angelo said that at the few number of or microscopical number of superposed objects, then the collapse is very weak. Yes. So if the incoming light is in a quantum superposition state of few photons, it is still a macroscopical, and also Angelo mentioned that photons have no mass and they are not suffering from gravitational collapse and so on. So we don't expect collapse here. So then a very curious question is that why we cannot see the quantumness or quantum superpositions of the photons and perceive it through our brains. But if there is a collapse somewhere, because once the light is detected, it is converted into some electrical signal, then it is no longer a light or photon. So whether the collapse happens somewhere here in the brain or through the neural channel, okay? So where the quantum collapse occurs, where humans cannot distinguish quantum world from classical world, becomes an interesting question, where the quantum collapse, spontaneous wave function collapse occurs in the human vision system. Is an interesting question. It's a different line of research that I will not go into, but there is a literature about that that you can find and dig into Google. There are good ideas and discussions about that. Okay, so when the light gets through the cornea and the lens and reach to the retina after going through this there is a gelatinous region between the lens and the retina, and after some photons reach to the retina, something happens to convert the light energy to electrical energy, and this is known as visual transduction mechanism. Okay, so this mechanism is complicated. It's a hierarchical sequential steps of different different stages of ionic migration, polarization, and switches. And it's a very beautiful description of how this happens in terms of chemistry and physics. But the Nobel Prize, so description of this visual transduction cycle is given to Wald in 1967. It was not a physics or chemistry Nobel Prize. It was given for, if I'm not wrong, either in medicine or physiology Nobel Prize. Okay, but it's a very hybrid interdisciplinary description. It has polarization, hyperpolarization concepts from physics. It has chemical concepts of ionic vibration and so on. But I'm going to only focus on the very first step of this transduction, which is known as isomerization. Okay. All right, so once the photons arrive to the retina, they interact with this rhodopsin and on these rod cells with the photosensitive molecules. So for us, there are two important molecular objects there. And one of them is called opsin. The other one is called retinal. Opsin is this larger one at the bottom. You can see some model of it here. Okay, this opsin is larger and retinal is the smaller one. So and when the photons arrive to the retina and interact with these photosensitive molecules in the rod cells, this retinal may absorb one photon, depending on efficiency or absorption coefficient. There is a probability that this photon will be absorbed by the retinal. So this can be envisioned like some biological photodetector. Okay? Then what happens as a result of this absorption? This light energy is converted to some mechanical type of energy. And as you can see in the right picture, this retinal makes some shape change. Okay? This conformal shape change of the molecule is known as isomerization. Okay, this is response of optical excitation of the retinal cell. And interestingly, this can happen at the single photon level. So you only need one photon to make this shape change. This isomerization only triggered by a single photon. So in 1942, Hecht and co-workers, 3 authors, wrote an interesting paper to answer the question that how many isomerizations, how many photons, how many trigger of these shape changes we need to be able to say that we have seen something. Okay, because if you just look at this picture, as long as this shape change occurs, if your brain agrees and understands this isomerization, you could be able to say that, okay, I have seen something. And then you are a perfect single photon detector. Then humans will be able to interact quantum technologies very efficiently and so on. But whether this is the case, if this single isomerization is sufficient to say in the brain and perceive that we really seen something, is another question. So we need a different threshold of seeing or perceiving the light at our brain level. So in 1942, this question is addressed by these 3 researchers, Hecht and co-workers, and they concluded that we need in the order of 10, or more strictly speaking, 7 or more photons or isomerizations we need to be able to say we have seen something. Okay. So this picture shows basically what happens. So first of all, in order to say I have 7 or more photons isomerizations at the retinal level, you should take into account that after passing through the iris and then passing through the cornea and lens, the photons will still be diminished through their interaction with the vitreous humor. This is the gelatinous substance that we have in our eyes between the lens and the retina. So we have very large amount of optical loss in this region. So you have to send more intense light at this level, like 100 photons. It just halves down, only half of it can reach to the retina. Okay, and once they fall into the retina, they interact with the molecules, photoreceptor cells, and try to do isomerization. It's a stochastic probabilistic event. So there's a certain probability that isomerization, this shape change, can occur. So this efficiency can be understood like quantum efficiency of a detector. And then if 7 of these isomerizations can happen probabilistically, the brain can say that, okay, we have seen something. And that was the idea of Hecht and co-workers. As they have 3 authors, they have this on the left, 3 sets of data, okay? So when they send these flashes of light to their eyes, they use their own themselves as human subjects. And then they said yes or no. It's like a machine learning, very simple classifier type of perceptron learning theory that you only may classify if it is dark, if it is light. If you see something, if you see a flash, you say yes. If you don't see anything, you say no. It's a very simple psychophysical type of experiment. Then their data is used to conclude that they need 7 photons per on the retina isomerizations. And modeling this experiment with incoming light, they decided that single isomerization is not enough. And then you need in the order of 10 or specifically 7 photons to say that they have seen the flashes. Okay, so their paper is called Energy, Quanta, and Vision. I don't want to say this is the very first paper that claims or investigates the threshold of vision at the quantum level. There are earlier works, but earlier works have questionable psychophysical methods and questionable detection methods, and this is the first rigorous study considered in this business. Okay, so then what we want to ask here. So number of 7 isomerization or 7 photon ability of our cells. At the single photon level, we can detect the light at the retina, but to perceive that we have detected something, we need 7. But still 7 is not a big number. We can still say that this is a very nice quantum object. And then we can put the 7 photons on the retina in some quantum states. We can even put them in superposition states. We can put them in squeeze states, entangled states, coherent states, Fock states, and so on. And then the question we want to ask, if this is at the quantum level, our eyes are probing retina, are probing human visual system, which is the window of the brain that opens to the real world. And also there are even medical researches through the retina. You can predict Alzheimer's diseases, you can predict other neurological disorders. So investigation of retina is very important, both fundamentally and also from biological and medical reasons. So if we take advantage of the quantum character of the quantum states of these 7 photons, can we do better to probe human visual system and perhaps in the long run, human nervous system? That was our research motivation. So we started to work on this question last year, funded by TÜBİTAK, and our efforts led to this paper. It is available in archive, and also we are happy that it's accepted for publication last month in Physical Review Research. So you can read through this, and if you're interested, I will not go into too much details, but you can write to me if you have any questions, and we can discuss more. I will mainly make an overview of our results published in this paper available in archive. So as I explained, very basically, our visual mechanism of transduction to convert this optical light signal to the electrical or neural signals. I said that there is a critical step, isomerization. Okay, so how to make this quantitative? How to make it more workable mathematically and physically? So we assume this is a binomial process. Okay, and then we say that there is a efficiency, a probability that isomerization occurs, and we say this is given by a number eta. Okay, so let's assume there are n photons fall into retina rod cells, and let's say n of them arrive successfully after going through the vitreous humor. After these losses, we have only n of them left on the retina. And let's say that K of the molecules go through shape changes. They isomerized. Okay. If this is a binomial process, this is then possibility of K of them successfully go through isomerization by the Bayes rule. Of course, you just multiply them. So we have eta to the K. But then the failure of the absorption is the 1 minus eta. Okay. Then that means n minus K of the photons were not able to cause any isomerization. And then we multiply these two with the rate of n of K binomial coefficient. Okay, this is binomial distribution. You can also say this is a conditional probability distribution of isomerization of K molecules under the condition that n photons arrived on the retinal level. So this is our mathematical model of a complex biological and chemical process. And let's now say that this n photons arrive to the retina can be in a different quantum state. It could be in a Fock state, it could be in a thermal state, it could be in a coherent state. In my talk, I will not discuss superposition states. I will only focus on simpler non-superposed states. But of course, you can say coherent state is also a superposition state of number states. But we are not talking in the sense that we have a quantum entanglement or quantum superposition in different degrees of freedom. So thermal distribution is just exponentially decreasing number of photons occupying the higher number of photon Fock states are less probable, while lower number of photons are higher probable, and there's an exponential factor, Boltzmann factor for this probability. While Fock state is very certain that you know how many photons you have, so you can say this is like a Dirac delta type of distribution, a spike at a given number of photons. So this is a 5-photon Fock state. Then we have the usual coherent state. So like a laser operating above threshold can be used for producing this coherent state. You can use flashlight for thermal state or sunlight. For the Fock state, you need a special quantum generator, a single photon state or Fock state generators. And then we can say practically all these states are experimentally available nowadays. So we are going to assume that we are not going to introduce vitreous humor, the loss of photons at the moment. And these distributions are assumed to happen at the retinal level. Okay. Later, I will also include the losses in the gelatinous region from the lens to the retina. But at the moment, let's assume that these three distributions possibly arrive on the level of retina. Okay. So my formula for K isomerization under the condition that n photons arrived becomes one more condition that these n photons will arrive depending on a distribution. So in this case, we just need to simply again apply the Bayes rule and then multiply the conditional probability of isomerization with the distribution or photon number probability with the n photons depending on whether it's coherent, thermal, and so on. Okay, so then we call this isomerization probability K. If there's an arbitrary number of isomerizations, so we just run K from 0 to infinity, and then our result here will just be a summation of all possible Ks. Okay. All right. So as a result of this arbitrary number of isomerizations, the molecules at the end of the visual transduction will be able to create some hyperpolarization, and then will convert this optical excitations into an electrical signal known as neural signal or photocurrent. Okay. So we are going to denote photocurrent with capital A, and we are going to assume, as typical in this visual system models, as a Gaussian distribution, a Gaussian probability distribution, a normal distribution for the photocurrent. Okay. So K isomerizations resulting in overall photocurrent of A given by this Gaussian distribution. So as you can see that the factor in front, the normalization of the Gaussian, has some vivid element. Normally it will be sigma square, but here we distinguish it to two terms. This is quite interesting because even if I use photons to excite these photosensitive molecules and cells, there's a possibility that there are thermal fluctuations in ambient conditions, in physiological conditions. So even if I don't send any photons, there will be sufficient number of excitations of photosensitive molecules that can cause a fake false signals, false detections, because we will again excite our brain that as if something has been seen. Okay, so it's like an illusion because there is nothing to see, but because of thermal fluctuations, our brain can fail and say that still there is something to see. And this is characterized by the sigma d. It's counted as dark count, or basically it is source is coming from non-optical fluctuations and excitations. The sigma a is the actual optical signal width, and for k isomerizations linearly increased, and then mean is also shifted by for k isomerizations from the average photocurrent A0 bar, and this is then becomes the usual Gaussian distribution, where the width has two contributions. One is the darkness count or failure counts, and the other one is the usual optical noise. Then again, similar to this arbitrary number of isomerizations that we summed over k number of isomerizations, we do the same, and we sum over k number of isomerizations to find the total photocurrent. Okay, so this is the main current created in our system, total current created after result of arbitrary number of isomerizations. Okay, so now what happens after these photocurrents are created? So then we have to assume how these currents are delivered to the nerve cell at the output of the human eye. There is a connection channel to the brain. And this is known as, in the neural network models, this is known as activation potential. Okay, so these photocurrents, if you multiply current with some transmittivity, you can find the voltage. This is very simple Ohm's law. So if you look at this formula at the bottom, you can see there is a product of W and A, and here A was the photocurrent. Yeah. So if you multiply current with some transmittivity, you will find the voltage. But there can be, it's a neural network. If you look at the retina, it's a network of cells. So on this right top corner, you can see some simple. It's like even a simplified picture of retina. There are many cells, many layers of connections. So you can imagine this is like a network. So then there are different resistivities or transmittivities, channels. We call them as weight factors. That's why it is denoted by W. Each weight factor multiplies the associated current, and you add them to find the total potential or action potential. Now here, our neural network model works on the assumption that this is a linear ohmic relation, okay? But we make it nonlinear, and we make it like a diode, and we treat it like a simple generalized perceptron model of neural networks, that beyond some threshold, this is when we say, aha, we have seen something, yes. So if the photocurrent or potential is less than a certain threshold, we say that we see nothing, okay? But if you pass this threshold, you say, oh, that, okay, I'm going to, I have seen something, okay? This is some threshold that Hecht and co-workers wanted to understand. So this is our mathematical model. We basically model, if you don't like the neural network language, you can think this is like a diode, yeah? So this is the linear part of the diode, and this is like a switch that you say yes or no. So this yes or no answers or psychophysical experiments can be modeled in a very simple level, intuitive level, like a diode action. So this is our model of this, this process, this experiment. All right. So you can see that this Pn is the distribution of the n number of photons. It could be Dirac delta, exponential, or Gaussian, depending on Fock state, thermal state, or coherent state. Then this light energy is converted to electrical signal. And this is also probabilistic because incoming light is has a random nature or probabilistic distribution. Then this action potential also becomes a distribution. Okay, so this is why we need to relate this incoming total photocurrent distribution to the distribution of the potential. Now this is a mathematical problem. It is very well known in random processes or random numbers. Okay. So what we do is that we basically, for example, if we have only two cells, what I mean by the two cells, let's say there are only two channels, W1 and W2, okay? So we have two photocurrents. Here there is only summation over two channels, two network channels. So in this case, we have two photosensitive cells, A1 and producing A1 and A2 photocurrents, okay? So if you want to find given probability distribution of this total photocurrent, what's the probability distribution of the action potential? You refer to the random variable theory, and the answer is given by a convolution integral or convolution of two signals. If there are many cells, then convolution becomes more involved. You have to deal with multiple integrals. So I'm not going to show it to you, but this is the very familiar signal theory response. Okay, so like a convolution of two signals, and to create the photocurrent action-induced photocurrent-induced action potential distribution. Now the question is, if the action potential is a distribution, then did we lose any information on the network structure? Because at the end, if I'm going to investigate the brain signals, if I'm going to investigate some optical responses and so on, and understand something about this complicated retina network, yeah, then this parameters transmittivities is basically your possible degenerative diseases, or maybe depending on your age, depending on your visual system problems, your transmittivities may be different than a normal person. Okay, by looking at the distribution of the action potential and the neural signals, and if you have a database of normal persons and compare it with your results, you can say that your retina or other your visual system has some problems. So basically, we look at the noise or errors in this distribution, and in the information theory, this is characterized by the Fisher information. So in our lectures, we have discussed basically in our lectures we have discussed the precision and derived the shot noise, for example, and said it was related to uncertainty relations. So if you have a distribution, with it can be seen as an uncertainty relation and can be related to the so-called Fisher information. So this is how we calculate the Fisher informations. The expectation value of this logarithm of the distribution, and you take derivative with respect to this parameter that you want to find out or estimate. Okay, so this parameter should be related to some estimator, an unbiased estimator, and then the variance or the noise standard deviation, as we have discussed, is always greater than or equal to reciprocal of this Fisher information. Okay, so it's very similar to a certain type of relations, and this lower bound is called as Kramer-Rao lower bound. It's a good information on the precision that you can have to find out this parameter W. So it's easy to understand at this single parameter level, but this is only true if you have a single cell here. Okay, so if you only A1 and W1. If you have multiple cells, the Fisher information becomes a matrix because all of them can be correlated and then they contribute to the noise. So you have to calculate elements of different channels. So let's say if you have two channels, so you have one error coming from here, one error coming from here, and they're also correlated. Okay, so you need 4 elements to characterize the covariance of this information matrix. So basically, you calculate the Fisher information for different parameters, W1, W2, and then if it is 2, you have 2 by 2 matrix. Then you can still write a noise bounds for these systems. You just need to take the inverse of this Fisher matrix, and then your bound is given by this relation. Okay, so multivariable generalization of this parameter estimation theory is trivial. It's just a lengthy calculation. Okay, so let me summarize, give you some examples of our typical results. So this is only for a single cell. So we use this simple formalism with only single scalar calculation, no matrices. And the result of this Kramer lower bound, basically the right-hand side, okay? For different choices of distribution function models, exponential, Gaussian, or the Dirac delta type of distributions are summarized here. So the red boxes are for the exponential distribution, thermal distribution. And you can see Kramer lower bound is always larger than the other two, where the green ones are for coherent. This diamond blacks are for Fock distributions, and Fock distribution has the lowest Kramer row bound. Okay, so this shows you that if I use Fock state light, if you go to a doctor and if they just send you laser light, a coherent light, if you ask them instead just use a single photon source, and then you can get more information about my eye. Yeah, so this is basically what it tells you. And this is for single photon level. So we have on the left only single photon. So you just need a single photon source here. While for the right one, we have 5 photons. Of course, this is not consistent with the hacked results which said that we need 7 photons or more. But this is a general behavior. Okay, so for numerically, we just stop here. But if you go to 10 or more photons, it's just numerically more exhaustive calculation, but you can get a similar trend. Fock states always perform better than the other two. And coherent states is intermediate, and thermal state is the worst choice to investigate human visual system. So for the multiple case, I don't want to go into details, but you just for presentation purposes, since we have many elements, larger matrices, we need just a single parameter to express the general result. So basically what you do is you map this covariance matrix to an error ellipsoid and calculate its volume so that you get rid of all the dimensionality effects and compare the volumes of different multiple variables. And if you do this, again, this trend continues, that the Fock states performs better in a 2-cell case as an example, or if you go to multiple variables, again, we find a similar trend, okay? So this is again similar behavior, and this is the area instead of, because if you have 2 variables, this ellipsoid becomes ellipse, so we talk about area, and you can see that again, this black diamond Fock states are at the bottom. So this is very similar to Kramer lower bound behavior in terms of this time, a multivariable parameter estimation theory using the error ellipsoid. And this is for 3 variable case. Again, this is our error ellipsoid, and these are projections on different parameters that we want to estimate. And again, the trend is the same. Okay, so then our conclusion is dependent of the dimensionality or complexity of the number of channels of your neural network model of the retina. Then what happens if we add more layers to the retina? Because if you remember this biological shape, biological representation of the retina, we have amacrine cells, we have ganglion cells, we have different cells in the retina. If we add these layers also and make more realistic models of the retina network, again, the trend continues, that again, the Fock state performs better. But interestingly, if the retina becomes more realistic and more complex, then it seems that the difference between Fock and coherent states gets not that significant. Okay, but still quantum lights are performing much better than the classical or thermal light. So then we also added, as a subtle reason, we added the beam splitter models to model the vitreous humor gelatinous cell, which causes some loss of the photons when they transmit from the cornea to the retina. There is a loss mechanism. So we use the standard beam splitter loss model to add this effect. And again, the result of this study can be seen here. It is very similar to more complex network model. Coherent and Fock states perform similarly. Fock state is a little bit better, and thermal state becomes progressively worse. If the network structure is also taken into account, this is the same trend. Okay. So when you add the complexity of the retinal network, when you add the also additional loss mechanisms, still you perform better than the classical light. Okay, so this is my conclusion then. We examined the methodological capability of different quantum states of light to probe neural network models of retina. And we have developed a formalism that allows us to add the losses and allows us to add the complex retina model networks. And then our calculations basically concluded that Fock state is the best choice to investigate the retina network model. But in the case of losses, in the case of more complex models are considered, the difference between Fock and coherent states are less, but still they both perform far better than thermal or classical light. So there are other studies that I should mention. What is the significance of our results? So in addition to probing retina, you can say that since our photodetection efficiencies depend on age, human conditions, and depend on person to person, you can also ask the reverse question. Once you probe the retina, you can use network parameters of the retina as a signature, biomimetic signature, and propose some biometric devices based upon quantum light. Okay. Another question that I didn't discuss here, that instead of thermal, coherent, and Fock states, you could consider superposition states as the input to the eye. And there are a little bit controversial discussions whether humans can detect entanglement, Bell states can be violated by human eyes used as detectors, and so on. There's a literature on this topic as well. And our systematic methodology can help on these discussions, and we are planning to continue investigating this. This is another example where an example experimental is proposed. So basically very similar to what you do when you go to a human doctor, ophthalmologist. They use this, you put your chin on a chin rest and then they send you light. So here again, they proposed in this paper that if we use structured superposition light, we can detect some anomalies and diseases in the human eye system. If we use spin orbit coupled structured light superposed states, these are Lagarde-Gauss type of modes of the light. So you can see there's spiral shapes. These are wavefronts, and using quantum light improve the precision and prediction power of these kind of ophthalmologic applications. Okay. So again, there are also implications of our studies in the wave function collapse models, as well as into this diagnosis of neurodegenerative diseases, because some thicknesses of this retinal network model layers are proposed in medicine, that they are some signatures of something is wrong with the also neural system. So if your retinal has, let's say, higher, larger thickness macula, and then this is usually studied by image processing. And if they detect that your macula is more thick than the other people, then they suggest that you have more prone to Alzheimer. And these are usually useful for pre-recognition of some neurological disorders. So these studies of using quantum light can reduce the requirement of lots amount of data and allows us, as we discussed in our lectures, allows us more ultra-high precision predictions. Okay, so if you are interested in this research questions, you can visit our web page, and we have other ideas and directions that in this vision and interaction of human visual system with the quantum light, you can see our web page. And thank you for your attention.
Thank you for this very nice talk. Can we now take several questions, some questions? Indeed, there are some of them in the chat. Can you read them, Özgür Hocam?
Okay, I'll try. Okay, so who is the first? Will you do the same work in owls or cats' eye cells and later compare with the human cells? Yeah, we just use them as our biomimetic examples. So indeed, there are two types of experiments you can do, either in vivo or in vitro. So in the case of animals, you can also extract their retina and then use it. And you cannot question them whether they see something or not. The advantage of humans that in the psychophysical experiments, you simply ask whether you have seen something or not. The analysis of this data is tricky because humans can lie or they can make false positives. So when they answer, so you have to model them more carefully than your usual quantum optical interferometric analysis. But if you do, then this is nice that you have some photodetector which can talk. On the other hand, in the case of owls, cats, or other eye cells, usually the method is extract their retina and use them in vitro. Yeah. And there are also some works on frogs or other animals also for retina. These are basically addressing the question of the threshold of photonic detection at the retina level, and then they are compared with the humans. And then this question is nice because this might be relevant to where the spontaneous wave function collapse occurs. So by comparing in vitro results with the in vivo results, you can decide in which part we lose the quantums. So there are some comparative studies in this direction. There is another question. To be able to use convolution, I think each Rhodes distribution should be independent from each other. Yes, that is right. We make some subtle assumptions that I didn't go into technical details. They are written in our paper. You can read them. But basically, we assume the number of isomerizations is far less than number of photons. And also at the same time, we assume that the incoming light, even if it is in different quantum states with different number of photon distributions, we assume there's a uniform wavefront. Okay, so you can assume independent behavior between the different cells. You are right. Okay, I don't see any other questions.
Yes, in the chat, maybe someone wants to ask using microphone. Please, welcome. More question, please. So it seems that there's no more questions.
Thank you.
Thank you. So perhaps we can close here this session, and we come together at 3 o'clock with another exciting talk. Please come at 3 o'clock. But for the time, I want to thank once again Özgür Müstecaplıoğlu. I want to thank all of you for coming. So see you at 3 o'clock.
Thank you. Thank you all. Bye-bye.